Alright, I'm going to have to try to shake off some rust. This will be my first video I've done since the pandemic, so bear with me on some of this. But this is lesson 1.1 of calculus. And this first unit, we're just going to be looking at functions and models. It's going to be a lot of review of what we did in pre-cal, except for, of course, a much faster pace. So I expect to spend about a month on this idea of functions and models and just reviewing what we did with functions back in pre-calculus. Today I'm going to look at 4 ways to represent a function. Okay, this is the first way. This is a equals pi r squared. We know that this is the area of a circle. And so I would say that this is being represented algebraically. All right, so this is being represented algebraically. We're just looking at it just being something that we did last year in pre-calculus that was very algebraic. And the way that we would talk about this, we would say that A is a function of R. Okay. Notice that the A came first right here. Is a function of R. R is on the business end of my equation, getting stuff happening to it. Okay. All right, next, we just have a table on this one. Okay, we just have a table. This is actually a table from, I believe, the population of the world, and from 1900 down to 2010. Okay, and so what we could easily do, we could come in here and we could say, all right, in 1950 right here, the population of the world was, it sounds kind of weird to say 2,560 million. So we would just say 2.56 billion. Okay. Whenever we look at this, we are looking at this function numerically. Also, I haven't written on a smartboard in 5 months, so you might have to bear with me on that as well. So we say, in this case, the population is kind of my y variable right here. So my population, so we say P, population is a function of time. Okay. So whatever my y variable is, that's whatever's on this right side right here is going to be what I'm going to put first, and whatever my x variable is, that's going to be what it's a function of. All right, going right through. Sometimes they just tell us about a function, like on C right here. They're just telling us the function verbally, and that's exactly how I would denote it. This is a verbal function. It says the cost C of mailing a large envelope depends on the weight W of the envelope. So there's no simple formula to connect W and C. The post office has a rule to determine the cost whenever W is known. They can go on to tell us more about that, but this is just a verbal model of what the function would be. Again, it would be cost is a function of the weight. And then we have, it says the vertical acceleration of A of the ground as measured by a seismograph during the earthquake is a function of the time elapsed T. And so I'm willing to bet on this next slide right here, yeah. And so here I have a visual model. I'm actually able to see the amount of, the amount of energy that's going out at a certain time during the earthquake right here. Okay, and so I'm just looking at this one visually. We looked at functions like all 4 of these last year. We had applications and word problems where we were told them verbally. Of course, we did graphing, we did algebraic, and then we also did tables, and we plugged it into our calculator. All that stuff is still going to be fair game this year in calculus, except we're going to take it, hopefully, many steps further. Okay. Now I'm going to go back to my toaster. If you guys remember my toaster last year, in order for it to be a function, what has to happen is each element of x has to go to exactly one element in f of x, okay? And so what happens is you have this independent variable out here. My independent variable x, which I used last year as a slice of bread. Okay, it's going to go into this machine. Okay, bread goes in, and what comes out is going to be called your f of x. Okay, or your dependent variable. Okay, and of course, the bread can only come out as one thing. All right, the bread can't come out sometimes as toast, and then it can't come out sometimes as lasagna. All right, it can't happen. The bread has to go in, and it can only be assigned to one of the dependent variables. All right, and so that's going to be that's how I'm going to know if something is a function or not. Now we're going to get a little bit more specific on this. Everything over here that we're putting into the toaster, everything that's over here that is an independent variable, I'm going to call that my domain. While whenever it comes out, it's going to be known as my range. So my toast, everything that's going to be a dependent variable that comes out. All right. All right, some ways that we're going to see this is we could see it definitely as ordered pairs. So just bringing this down right here, this is just like the ordered pair 1, -2. Okay. And so by the time I take all the ordered pairs, every input that leads to an output, every independent that leads me to a dependent, I get all those points, I'm going to have a graph. Okay. And so that's going to be the first thing I want to do is I want to look at this graph. I want to be able to find the values of f of 1 and f of 5. Now, a little bit of insight right here. This 1 and 5 is going to be my input. These are going to be my independent variables. So my independent variables, what I'm looking for on this is to find out what my dependent variable is going to be. So I'm putting 1 into the toaster, and I'm seeing what it comes out as. So whenever I put in 1 into the toaster, I'm going to go this way, and I put 1 into the toaster, and it came out as the number 3. So f of 1 would equal 3. And yeah, we can make that a little bit simpler because look, right here, I'm just going through the point 1, 3. Okay, let's do the same thing with 5. You go ahead and plug in 5, see what you get. Guessing about -7/10. So close enough is going to be good enough on that. Don't call it -1, but make sure you're bigger than -1/2 because we're definitely in between right there. So close enough is going to be good enough on that. Again, I came over to 5 and I went down less than 1 unit, so I'm good right there. Domain and range. Domain and range. Another way to think about domain, remember, it's everything it's all my inputs combined. Or in other words, it's what can x be? And if I'm asking myself what can x be, I'm still wanting to look at it as I'm still wanting to think of it in terms of not set builder notation. That's how that the book might put it, but I'm wanting it as interval notation. I want to know the smallest value that x can be. Right, if I come over here, I came all the way back right here to 0. And I can see that x touches every single value all the way until, let's see, there was 7, 8, 9. So it touches everything from 0 until 9. And to show that it touches 0 and 9, I'm going to be using a bracket on it. Okay? I could use a parenthesis there if it wasn't touching but going right up to it. Maybe we'll see one of those in just a minute. Okay? Range, I'm just going to change it to what can y be? All right. What all outputs do I have? All right. Sometimes it came out toast. If I put in a Pop-Tart, it comes out a hot Pop-Tart or whatever. What all can the y values be? So I'm going to do the same thing, but I want to find my smallest y value right here. It comes all the way back to -2. And then as you can see, it touches every y value all the way up until this peak right here, which is at 1, 2, 3, 4. So it touches every single value from -2 until +4. And it does actually touch -2 and +4. We'll come into several with vertical asymptotes, horizontal asymptotes that do not go all the way and touch it this year, but that will be later, maybe on in your homework. Now we're going to go over all the parent functions again, all right? All the same ones we did, and we're going to do all the transformations on it. That's later on in a different video, okay? So some of these basic parent functions, though, you know, we're seniors, we're taking calculus. I'm going to expect you to know what this is right here. F of x equals 2x minus 1. Y equals mx plus b. It's a linear equation, okay? And so I'm going to go to my y-intercept right here. Is at -1. And then this is my slope. I just rise 2, run 1. Rise 2, run 1. And so I'm going to get this nice, healthy line. It goes up and down. And it's wanting the domain and range on this. Now, the domain on this, as you can see, these arrows go left and right forever and ever, all the way to the smallest value I can think of, -infinity, and all the way to the biggest value I can think of, +infinity. Okay. And so I'm just going to write that as in an interval notation. And we can't actually touch infinity. Infinity is more of an idea that we're not going to be able to obtain. So infinity always gets a parenthesis in here. Now, I'm thinking of my seniors this year. I know last year we played a little bit with the notation of double barred R, which means all the real numbers, every fraction, everything that doesn't have an imaginary element to it, we can write as double barred R. So either way you want to write it, you'll see me flip back and forth between both of them. Range is going to be the same thing. As you can see, the smallest y value this thing is going to eventually touch is -infinity, and it touches everything up to +infinity. Okay. So we go -infinity to +infinity. Or you can write your double barred R. All right, I'm going to let you guys do part B. Hit pause on the video. I got to figure out how to hit pause on the video. I'm using something new this year. And so hit pause on the video, come back, and we'll see if we can match up answers on it. Okay, that didn't go like I thought it would. We'll just roll with it. So hopefully on this guy you drew your U. I apologize, my smartboard is just a tad bit off on this. But ideally I went to the points -1, 1 and +1, 1. And more importantly, it makes it so my domain is going to be, again, all real numbers, because I'm going to touch everything to the left and to the right on this. While my range, be careful, the lowest value that it touches is going to be this 0 right here. And it actually does touch 0. As you can see, it just keeps growing, growing, growing all the way up until infinity. Okay, let's review our difference quotient. We saw this briefly last year. We're really going to take off with this difference quotient this year. Okay? My difference quotient is, and this will be given to you, my difference quotient is defined as f of a plus h minus f of a all over h. And we're not going to shake this for a while. When I say a while, I'm saying probably the whole first quarter, maybe some of the second quarter. And whenever we do this, we need to think about this in three parts. Okay, part one is this f of a plus h. What's going to happen is I'm going to take this a plus h and I'm going to plug it in to both of these x's right here. See what that looks like. Just took out the x, put in a plus h. That's step one. Now, there's three steps on this. The steps get easier as we do each one. Okay, step two on this is going to be subtract off my f of a. So not f of x. So now I'm going to take this just a and plug it in for both of these x's. Now I'm going to subtract off the whole thing. So I'm going to put it in parentheses so that way I don't goof myself up. Because you're going to have a checkpoint here in a minute. What color have I not used? Blue. Step three, the easiest step of them all. I'm just going to put everything over h. And everything over h. Now my goal now is going to be to clean this up. Get rid of all the parentheses. There's going to be a lot of stuff that cancels. I'll show you exactly what cancels in just a minute. So the first thing I'm going to do is I'm going to expand this binomial. Okay, so I'm going to square the first term. Take the product of the two, AH, and double it, and square the last term. Kind of wondering what I did there? I did some foiling real fast. It's one of our special foiling patterns, A plus H times A plus H. Since they're the same, it'll follow that pattern every time. Distribute the negative 5. It was negative, wasn't it? Yeah. And then distribute the negative over here. You might be thinking, man, this looks worse. It does kind of look worse for now. And then the h just kind of stays put. Now I'm gonna skip a step here. I'm running a little bit low on space. I'm not managing my space very well at all, but I think you'll see what's going on. Is everything that does not have an h now should cancel. It's like the positive 5a and the negative 5a gone. The negative 1 and the positive 1 gone. I've got a negative 2a squared right here, and then a positive 2a squared, because that 2 is going to eventually distribute all the way through. I get to there, every term that's left has an h in it. So if I distribute that 2, I get 4ah plus 2h squared minus 5h all over h. A couple ways to think about this. I can divide each of these terms in the numerator by h, or you can just simply factor out an h. This way seems to strike a chord with most people a little bit better. So I can then cancel out the h's that I pulled out. That should happen every time, because remember, every time I start canceling right here on this step, everything that doesn't have an h cancels. So I will always be able to factor out an h right there, and I get my final answer is 4a plus 2h minus 5. Don't shake this off. This is going to be, I'm willing to bet it's going to be on your first quiz, and that you will see it again, of course, on the test. And we're going to see it probably on the first 2 or 3 tests in here. So don't shake this off. All right, representations of functions. So kind of just a review. This is kind of where day 2 would start. If you're getting kind of, if you want to stop the video, go work some problems. We're about halfway through right now. And so kind of just a review of what I did the first part of this video. I described functions all of these ways right here. So I want to go to the verbal model. I want to look at it. Okay, I turn on a hot water faucet, and the temperature of it depends on how long the water's been running. Now let's just say you don't have one of those like infinite hot water heaters on this, okay? I'm going to draw a rough graph of t as a function of time, little t, that has elapsed since the water was turned on. Okay, so I get in the shower. I probably don't get in the shower right off the bat. Probably what I do is I turn on the water. Why do I turn on the water when before I'm in the shower I'm giving one of my sons a shower? Well, it's because the water's cold. I don't want to get in there right now. So I'm just going to mark a line right here to determine cold. That's the starting temperature right there. Okay, notice I'm not being just real exact with it because I'm more interested in the shape of this graph. Now, after I turn it on, yeah, it's going to be pretty cold, but by the time the hot water goes from the hot water heater to the shower, stuff's starting to get warmer. Warmer and warmer and warmer. And then finally, you reach that nice temperature that you always want. You can't stay in there too long. The temperature starts to drop again. All the way back to where it started. So it doesn't go down there just drastically, but over time you'll start losing more and more hot water, and then you're back to where you started, just the regular cold water. And so this would be a graph of the function of the temperature as a function of time. Again, it's not going to have to be exact. Yours might not look exactly like mine. Same way with the homework. They're going to have you draw some. Yours might not look exactly like the way we're going to do it in class, but close enough is going to be good enough on this. All right. So that's turning a verbal into a visual. Let's turn a verbal into a actual equation. So we have a rectangular storage container. Oh man, getting broke in right. The storage container. It's going to have an open top. I apologize, my lines aren't connecting. It's a little bit off, like I said. Has an open top, and the volume of this whole thing is going to be 10 cubic meters. I'm going to write that up here. Volume equals 10 cubic meters. Cubic meters doesn't necessarily need that. And the length of the base is twice the width. Okay, length of the base is twice the width. The material for the base is $10 per square meter. The material for the sides costs $6, so that the base is going to be a little bit thicker. Express the cost of materials as a function of the width of the base. So I only want the cost in terms of the width. So let's just start with the area of the base. Area of the base, we know is going to be area equals length times width, because it's a rectangular storage container, so it's length and width. Okay. However, it tells me in here that the length is twice the width. So I could get rid of this length right here and just call it twice the width. And we'll do the same down here. Twice the width. So the area of my base is actually going to be 2w squared. So I can actually do my cost function as well. My cost function is going to be, well, it costs $10 per square meter on the base. So my cost function is going to be 10 times 2w squared, which is going to be 20w squared. Now, we're not told much about the height. We know it's there. And so if I look at the sides, this side's going to be w by h. The front side is going to be 2w by h. And of course, this side over here that you can't see, it's going to be also w by h. And of course, the back side is going to be 2w by h. Try to get it on there. Side back there. So what happens is I have 2w by h's So by the time I add all these up, I have a WH, two WHs, three WHs, that's 5. Okay, all in all, that's going to be 6. One way or the other, I have 6 WHs. And that's going to be the area of the sides of this storage container. Okay, the cost of each side is going to be $6 per square meter. So if I multiply that by 6, I'm going to have to use $6 for the whole area right there. It's going to be 36 WH for the cost. Cost of sides. So all in all, I've got my cost ready to go. My cost as a function of the width is going to be 20 W squared for the bottom plus 36 WH for the sides. Now we're close. Problem is we have an H in here. If it's a function, we're only allowed to have the dependent on this side and then the W on this side. This H right here, it doesn't want the H in there because it just wants the width. Okay? So I'm going to play with that a little bit. I haven't used one piece of information on here. I haven't used the fact that the volume is 10. So to find the volume of this rectangular storage container, it's going to be length, which is 2W, by width, which is W, by height. If I multiply those three together, I should get the answer to be 10. And the variable I'm trying to get rid of is this H. So I am going to solve this for H. Okay? So I'm going to divide both sides by 2. I get W squared H equals 5. And then divide by W squared. H is actually equal to 5 over W squared. So now I can plug this in for H. I get my cost function. 20 W squared plus maybe 36 W times 5 over W squared, which will simplify to let's see, 36 times 5. Ooh, it's awfully early. 180. And then I got 2 W's on bottom. So I got W right there. Of course, W cannot equal 0 and because it is a length right here, so we're not really worried with that W being on bottom. And it actually has to be a positive number because we can't have a negative length. And so a little bit of a relevant domain on this. W needs to be bigger than 0 in order for all this to work. So a lot of work right there. That's going to need some practice. So we'll find those in the homework and we can hash those out together later on this week. Okay, let's go back and talk about domain. We had some things that hindered our domain from being negative infinity to infinity. We always wanted our domain to be negative infinity to infinity, but it rarely happened last year. Okay, and so one thing that we looked for was in this first problem right here, a square root. All right, let me get rid of squared and let's just say an even root. If I have an even root, remember this is later on, but that's just going to be the graph of a swoop. Right? The graph of a swoop cannot go over here into the negatives, meaning that whatever is underneath my square root, I said my swoop, has to be greater than or equal to 0. Well, if I just solve this for x, I'm going to subtract 2 from both sides. I get x has to be greater than or equal to negative 2. And I still like the interval notation on this. Greater than or equal to negative 2 means that I want all the numbers that are between negative 2 and infinity. So I like this answer. The back of the book might do something called set Euler notation where it says x such that x is greater than or negative 2, where x is an element of the real numbers. Something like that. I did not teach this last year. I am perfectly fine with this negative 2 to infinity. Now, the second thing that we looked for on this was denominators. If I had denominators, that is where my vertical isotopes were. And what I know about vertical isotopes is that I don't want to divide by 0. That's just a spot where it's not going to be defined. Okay, so I want to make it so that my denominators don't equal 0. I don't want that divide by 0 error right there. So I want them not to equal 0. And so I just want to solve this, like solve this quadratic. Get it factored. I think that's the easiest way. And so that means that x cannot equal 0 and x cannot equal 1. Okay. So it can equal anything other than these numbers. That means it can equal anything going all the way down to negative infinity, all the way up to 0. It can equal anything between 0 and 1. Now, I've had people argue with me before. There's nothing between 0 and 1. Oh, there is. There's 1/2, there's 3/4, there's 7/8, there's 1/4, all those. And it can equal anything between 1 and infinity. Okay? And then we're going to throw these unions in there. Remember, those unions just mean or. Okay? And so that's how we wrote it last year. I still like the interval notation. Okay? Now, the good news is it gets a little bit easier to tell if something is a function or not using a vertical line test. We had 2 tests last year. We had a vertical line test and a horizontal line test. The vertical line test told me whether or not something was a function. All right? Horizontal line test told me something about being 1-to-1 and being able to find the inverse of it. So we're just going to do the vertical line test right now. And it said that a vertical line test is going to work if and only if no vertical line intersects the curve more than once. So doesn't matter where I draw my vertical line, I'm only allowed to touch my graph at one spot. As you can see, this would be a function right here on the left. Over on the right, I'm good with these vertical lines. Look, I'm not touching the line more than once, but once I get to where this pink line is right here, that's a no-go. Since that happened, this graph right here on the right is not going to be a function. So let's draw some of our own graphs and use a graphing calculator to help you on this. I'm going to just kind of show you how to do this just mathematically by hand. Okay, and so x equals y squared minus 2. Let's see, I'm trying to think how far we made it last year during the pandemic. We did cover conic sections last year. This was a conic section in which I had a parabola, since only one variable is squared, and it's being moved to the left 2. So I could definitely draw a parabola that's opening the wrong way. That's been moved to the left 2. Let's try to make more sense of this though. I'm going to go ahead and add 2 to the other side, and then take the square root. And so this might make a little bit more sense to you. The fact that we had the swoop. And again, I'm going to go over all those again later on. This is just kind of getting an idea of what the graph's going to look like and applying the vertical line test to it. I'm inside the function here plus 2. So I'm going to move it to the left 2. Well, it looks like it is going to pass the vertical line test. But remember what I said just a while ago, that I should have a parabola on this. Let's see where the parabola comes from. I just took the square root to go from here to here. Yep, Mr. Lovelady forgot the plus or minus. Didn't forget it. I was going to see if you remembered it. All right. So yeah, I got the reflection of this swoop as well, making it so it's a no-go, does not pass the vertical line test, not a function. Not a function. I'll let you play with some of those. Piecewise defined functions. A piecewise defined function is going to be a function that's, of course, defined in pieces. Okay? It wants me to evaluate and sketch. Sometimes it's easier to sketch first and then evaluate. I don't know, whichever way you want to do it. Okay? I'm going to sketch it first. I'm going to work it a little bit backwards. Okay? It wants me to sketch these graphs. Now I'm going to rewrite this as negative x plus 1. Because again, they're going to be basic parent functions or straight lines that you're going to be working with for now. Appreciate it while you've got those for now. Okay, so I'm going to come up 1, and I got a slope of 1. And so I have this function. That's been off a little bit too long. All right, let's try that again. So I'm going up 1. Oh, so much better. Okay. So I get this nice line right here. Okay. But in order to make it so it's a function still, it only wants a piece of that line. It only wants the piece of the line that is smaller than negative 1 right there. So all this hard work I did over here, don't need it. Okay. It goes all the way up to that line. And then it wants, I'm switching colors a little too much. Okay, then it wants the x squared if x is bigger than negative 1. Well, we talked about x squared just a while ago. That's going to be this nice parabola that comes all the way through. However, I only want a piece of the parabola. Okay, so this whole part of the parabola up here, I do not want it. I'm going to erase that. Oh, I'm good. And so this is what my piecewise function would look like. Now from here, I can go back to do what I did in the first example. I can say f of negative 2. Well, I can just come over to negative 2. I see I'm at positive 2. So f of negative 2 would equal positive 2. Is that right? I think I got off on it. I did. This line should be a little bit further up. Can I move it? Does it move? I'll show you a more foolproof way. So f of negative 2 is actually at 1, 2, positive 3. And what I can do on this is I can find the piece that it belongs in. This negative 2 right here is less than negative 1. So I got 1 minus a negative 2, which, yeah, sure enough, is going to be a 3. So I just plugged in negative 2 into that x. F of 0. Well, oh, sorry, I skipped 1. F of negative 1. Well, negative 1 is going to still go in this piece right here. So I can do 1 minus a negative 1 is 2. There's my 2 right there. There's where it landed 2 units up. F of 0. 0 is bigger than negative 1. If I look at my graph right here, f of 0 actually came out to be 0. Let's plug in 0 in for this x, see if we get the same thing. And we do. So again, a very well-drawn graph will help you get those function values. If you don't feel like you drew your graph very well, you can go back and plug it into your equation up here at the top. Now, a special piecewise function is our absolute value function. I want to go over it today. So we have the absolute value of x. I can rewrite it as in terms of x if x is greater than or equal to 0, or negative x if x is less than or equal to 0. We know from last year the absolute value function looks like a v, right? Well, the piecewise graph is actually breaking right here at 0, right there at that vertex of the v. And if you look at it, everything to the right is following just my identity function. Absolute value of x equals x. It's just a diagonal line that's going through the origin. Whereas everything that's to the left of 0, it just follows a slope of -1 that, again, goes through the origin. So that's where that comes from. Some people have trouble with the idea of, Mr. Lovelace, how does this make sense? You're taking the absolute value of something, you're telling me the answer is negative? I actually am. I'm saying if you take the absolute value of -7, we know good and well that our answer is going to be 7. All right, let's talk about using this piecewise function, how to get there. I plugged in something negative into this absolute value function. If I plug in something negative in the absolute value function, I have to use this bottom piece right here, which means that I need to throw a negative in front of what I plugged in. So I need to plug a negative in front of that -7, and that is how it turns back to be a +7. So hopefully it all makes sense. If not, come see me. It'd be much easier to describe that in person than what we're doing on here. All right, let's talk about coming up with our own functions. I'm just gonna make one up. Now it's gonna be pretty basic. Ooh, I'm trying not to give you any curved lines on this. So first thing I want to determine is how many pieces does this graph have? I'll go back and count it. I can count 1 piece, 2 piece. I'm counting 3 pieces on it. Okay, so that means that my piecewise function needs to have 3 pieces in it. I'm just going to work left to right on this. So let's start with this green line right here. Okay, it's a straight line, so and it goes through the origin. So I'm just going to count the rise over run on this. I rose 3 and ran 2. So it should follow the function 3/2 x, and then there's a +0 because it didn't actually go through the y-intercept, the y-axis. So I'm going to erase that part. And it's going to follow that f. Let's see how long this green piece is right here. X is between 0 and 2. Got that backwards. It's good to make mistakes, right? Even I make mistakes on counting and listing numbers from smallest to greatest. All right, let's look at this red piece right here. Again, it's a straight line. Now, this is going to be a little bit trickier. I think this red piece is going to be the hardest one. Maybe I shouldn't have just made one up. It's got a negative slope. I see that's going down. And let's see, it went down 1 and ran 1, 2, 3. So -1/3 on that slope. Now, the tricky part is going to be getting your y-intercept. We might have to just say close enough's good enough on this. We can do better than that. So that means if I was to rise 1, run 3, it would eventually go through right here, giving it a y-intercept of 1, 2, 3 and 2/3. And that, ladies and gentlemen, is why I don't come up with my own problems. I like to have nicer numbers on that if you're having to extrapolate. Now on this one, it's gonna carry this. It's going to be able to follow this red line whenever x is between 2, 3, 4, all the way to 5. And finally, we have the black line right there. The black line is the very first parent function that we went over, or that we will go over, first one we did last year, and it's just a constant function. It doesn't matter where I'm at on that black line, my y value, my output is always going to be 2. And that holds true from everything from 5 and above. like doing this in reverse as well. You know how I feel about problems working forwards and backwards. I like the way that goes. All right. All right, talk about symmetry. And then we're going to be done. Again, if you're watching this all in one day, this is 2 days worth of notes in class. So don't get overwhelmed by this. Hopefully we're doing a lot of this stuff in class. I'm just putting this out there in case that you miss. That's my goal this year, is to get all your videos up and going. So we'll see how that goes. So biggest thing you got to know about symmetry, there's 3 different possibilities. The first one is known as even symmetry. And I'm going to have even symmetry if f of negative x is equal to f of x. Okay, what does that mean? It means that, according to this graph right here, that if I go over negative x units, negative 2, negative 3, negative 5.5, whatever that is, I should go up as far as if I went over to the right x units. 2, 3, 5.5, whatever numbers I just said, I don't even remember. I should go up that same distance, all right? And so that makes it so that it is symmetric with respect to the y-axis. So an even function is going to be symmetric with the y-axis. That's easy to tell. Okay. Now, we also have an odd function. I might have to draw one. I really like that example of drawing it a while ago. So in this case, f of negative x is equal to negative f of x. We call that an odd function. If I have an odd function, I'm just going to think of the most basic odd function I can, is x cubed. Okay. I still missed that in the middle. You've got to be kidding me. No? Oh, there's one way to get out of it. Let's go back to percent. Now, an odd function is going to have symmetry with respect to the origin. So that means whatever you see in the first quadrant has been rotated 180 degrees, and you see the same thing in the third quadrant. Same for second to fourth, or fourth to second. Okay? Trying to make sense of it from this box right here, again, if I go to the left, say negative x units, it means I should come down to, say, I'm just going to make up a value, negative 4. Whereas if I went to the right, the same amount of units, let's say x units, it should go up on my y-axis to positive 4. Okay, so everything is just, all the negatives became positives, all the positives became negatives, but that's how you kind of test for it. I'm really going to make use of these boxes right here in order to determine if it's even, odd, or neither, just from doing this algebraically. I'm going to try not to do it looking at a graph. I'm going to try to do it just by looking at it. Again, I'm having trouble pausing this video today. Feel free to pause the video and try this. I might have you pause it. I don't think it's going to work, me writing on it and then going back. Ooh, it might. Just thought of something. Okay, so whether I'm testing it to be even or odd, my first step is always the same. What I want to do is I want to rewrite my function with a negative x in there. So that means I'm going to take out these x's and put negative x's in their places. My favorite thing to ask right here on the second day of school is, what is negative x times negative x times negative x times negative x times negative x? And all of them say, well, that's 5 negatives, so the answer is going to be negative x. Partly true. All right, if I do multiply 5 negative things by themselves, I do get a negative. You're exactly right. But also, if I multiply x by itself 5 times, I get x to the 5th. Don't forget that part. Minus x. My goal, whether I'm doing even or odd, is to make it look like it did in the beginning. And sure enough, if I factor out a negative, I make it look exactly like it did in the beginning. But I have a negative out there, meaning that I got the opposite of what I started with. Go back in your notes and look at what we just drew a box around. I got my f of negative x to equal negative f of x, meaning that this is going to be an odd function. I'm going to pause the video and let you guys try to work b, that g of x, and you work it through, and then we'll come back and see if you match the same answer as me, if I can figure this out. Give me just a second. Here. All right, I got it to be an even function. Remember order of operations on this. I have to take care of this. I got to take care of this exponent before I do any multiplication. So I'm going to do negative x times negative x times negative x times negative x, which gave me a positive x to the fourth. Distribute the negative, and sure enough, I ended back up with my g of x. You can definitely check this. Plug this into your graphing calculator. You're going to get something that's nice and symmetric over the y-axis, and you're good. All right. You see all my recording. I'm seeing how long I talk. It's a long time. So I think if I click off here, go back to present. Is it going to stay? That might work. All right, let's look at part C together. I think you're kind of seeing what's going to happen on this. Let's do one that's going to be neither on this. How can I tell that it's going to be neither? Okay. First off, again, I'm not going to know it's going to be neither if I'm working this on the quiz or the test. So I'm going to take negative x and I'm going to plug it in for all the x's in that function. And then simplify. Order of operations and simplify. So a 2 times negative x is negative 2x. And then a negative x times a negative x is a positive x squared. Distribute the negative. Oh, I almost ended up with what I started with up here on my h of x, except for I got this little pesky negative right here in front. So I'm going to factor out a negative. And let's see what happens with that. If I go back to what happened over here on part A, I almost ended up with this again, except for now I have a positive right there. There's no way to make all the signs match on this on part C. So the answer on this would be neither. All right, I've got all of them graphed from the previous 3 examples. So here's A and B and C, and as you can see in part A, I am symmetric with respect to the origin, so that makes sense for it to be an odd function. On part B right there, I am symmetric with respect to the y-axis, so that makes sense for it to be an even function. And on C over here, I am not symmetric with respect to the y-axis. This y-axis right here is not cutting it in half. And it does not have rotational symmetry. So sure enough, yes, that is going to be neither. Easy way to check your work on that. Okay. Increasing and decreasing functions I will get to. You can definitely read through this if you want to, but I'm going to skip that for now. Here's some problems I'm going to try to model the quiz after this first quiz. And so you're more than welcome to use this, of course, on your quiz. And so we'll also have a day this week where we get to ask questions about these problems